Curculents, welcome to it. This is Learn Extra Live with me, AB, Abraham with John. How are you, John?
Abraham, I'm really good, and it's a pleasure to be here again this afternoon.
Likewise, it is National Science Week. I hope all the mindsetters are doing something at their schools or just in their classroom, or even right now as you're joining us. I hope you're doing something that has to do with science.
Yeah, absolutely. National Science Week, great opportunity to look at science careers. And I mean, if you're in grade 11 and you're doing physical science at school, must be on your priority list. Hey guys, if you're getting good marks, get into the universities, find out when their open days are, because you need to get your applications in early next year. So don't be restricted, and remember, most of those faculties are going to take your grade 11 marks as entry requirements. So put in the hard graft now.
It starts now. Talking about that, let's start now. What are we talking about today?
Okay, so Abraham, what we're doing is we're doing electric circuits. Now, electric circuits, I love circuits. They're just amazing. You remember last week we spoke about electromagnetic induction, electromagnetism. Now we're going to move on to something that you're going to get in your matric exam. I can promise you now, even though the exam requirements haven't finally been written for your matric exam for next year, they're going to have a circuit. They've had them for the last, I don't know how many years. So you need to study this, because you might not have time next year to go over circuits. They've traditionally been in the grade 12 exam. I don't see why they won't be in next year. So guys, pay attention. We're dealing with some other interesting characters this afternoon. We're dealing with not Michael Faraday, but George Ohm. And George Ohm, he has a whole practical experiment that you're going to need to do in class as a practical. If you're not sure about it, we'll cover it here, so don't go away.
All right, don't go anywhere. Here's your toolkit. All you need to do, number one, is to join us via Facebook. Our Facebook page is facebook.com/LearnExtra. You should be knowing it by now. We have more than 48,000 likes, and you can join the crew, join the club and our community, and let's get chatting and also help one another on the page. Secondly, join us on Twitter. Follow us at LearnExtra. We'll try and read some tweets as the show progresses. And lastly, you can download your notes all for free on our website, which is learnextra.co.za. And now, beginning this lesson, here's a quote from a mindsetter who just said earlier on. Please, AP, may you share this quote for us? It says, not that I'm a genius, but one thing I always try to do is that I spend most of my time trying to deal with the problem. So try to deal with the problems that we are facing today on a positive note.
Excellent. Now, guys, if you've got problems, there's only one place to go to get the answer. That's the help desk. And we're starting a new way of doing the help desk. So get onto the website and fill in the form for the help desk. It's help desk on the web page. Get the form filled in, and we'll be taking your responses there. The other thing that I wanted to mention just briefly as Abram was going through his stuff is that you really need to make sure that you download the notes. Some guys have sent to me on the help desk, hey, download the notes. How do we do it? We're not sure. So what I want to say to you, you get onto that website and you look for the blue box. It says notes in it. Click on the blue box and you will get the notes. Okay, so don't forget that. Today, electric circuits, let's go. We're not spending a lot of time on the introduction, but in this lesson, what we're going to do is we're going to look at the three basic things relating to electricity. We're going to discuss current, potential difference, which is also called EMF. We're going to look at Ohm's law. We're going to explore that. We're going to talk about ohmic and non-ohmic conductors. We're going to look at resistors and how they're put together in series and in parallel. And we're going to look very briefly at power in a circuit. So you can see there's a whole lot of stuff, and I better stop talking because I can get carried away and I want to get through the stuff that we need to get through. So let's get our heads down and let's get going, because some of it's a bit of a revision. So let's start. Well, what do we understand by current? Everyone says current, you must beware of current. That's true, because current, what is current? Abram, you got any idea? What's current?
I say electricity.
Electricity? Not sure? Okay, so guys, what we're talking about, electricity is a movement of charge. Current, in revising from grade 10, we say current is a flow of charge that is either positive or negative charge. So what we've got to make sure of is that when we talk about current strength, how strong is a current? When you talk about currents, maybe you're thinking not just of electric currents, but of currents in a river. You know that if you dive into a river, you'll be swept downstream by the flow of the water, the movement of the water. Or if you're in the sea, you can get swept out to sea, even though there are waves coming in, by currents in the ocean. And they're very dangerous. That's why we have lifeguards on the beach. So it's a movement of water in a particular direction. Now, in terms of our current in electricity, it's a movement of charge. Now remember, there are both positive and negative charges in every bit of matter. The positive charges, objects, are called protons, so they're known as protons. And the negative charges are known as electrons. They come from the atom. Now the actual protons don't move. They stay stationary. But because the negatives are moving over them, they move in, it kind of gives the impression that the positive region of charge moves in the opposite direction to the negatives. That's why we have something called conventional current, which we will define a little later. We'll say conventional current. In fact, we defined it last week, if you remember. It's the movement of positive charge from a positive to a negative. And we're going to use this formula. I is equal to Q divided by T, where Q is the charge and T is the time, to work out the strength of the current. So if we've got lots of charge in a small period of time, it's like walking the talk. I don't know, did you participate on Sunday? There was a big walking race or a competition.
I saw that one.
You saw it?
One, but I wasn't
okay, so
participating.
guys, I was part of that. Crowds walking past a position, along with the deputy president of the country. I was there early in the morning, and we walked down the road. And sometimes the road couldn't hold everyone because there were so many people passing a particular point. Okay, earlier in the 15 and the 20 kilometer race, they were more spread out. So you had fewer people passing a particular point. The current wasn't as strong. Come to the 8K walk, which I walked with along with another 22,000 people. We moved quite quickly, but a lot of people covered a short distance. It was like a high current. If you just stood there, people would almost push you forward. You'd feel the current. Okay, now, what is potential difference? Potential difference is defined as followed. Potential difference between 2 points in a circuit is the work done to move 1 coulomb of charge from one point to another. Hey, now that's getting a little bit difficult. It's about energy. These charges carry energy. So I want you to think about walking the walk. And if you're going to walk the walk, you need to have some stored energy. I've got lots of stored energy. I eat well, and I've got a good padding around my middle as well. So there's my internal supply of energy. But you know what? Afterwards, I still felt a bit tired. I needed to take in some sustenance to recoup the energy. That's what potential difference is all about. It's about the energy required to move through the circuit, between 2 points of the circuit. So it's how much energy, how much work. Work, remember, is the ability to, energy is the ability to do work. So if I've got stored energy, potential energy, I'm able to do work. So in a circuit, we recognize potential difference between 2 points is determined by the amount of work done per unit charge. So I might not have 1 coulomb of charge to push through a resistor, might not have 1 coulomb of charge to go up a hill. A resistor is like a bit of a hill. It's stopping you moving freely. Okay, I might only have half a coulomb, or even a tenth of a coulomb, or 100th of a coulomb of charge, because a coulomb is a huge amount of charge. What we're wanting to do is to work out the energy before and after, the difference in energy. How much have they done before they started? How much did they get after? The difference between that amount of energy. It's like taking a dipstick. Imagine if you had a fuel tank, and I haven't got one of those. You could put it in, and you could say the fuel level's this high at the start, and it's that high at the end. So the difference in energy is the amount of work that's been done. Hope you've got that. Very important idea, and you'll see I've stressed potential difference, because when we come to measure potential difference, we use something called a voltmeter, and the voltmeter is always connected across the thing that is doing work, so we'll say it's connected in parallel. We'll have more to say about that at another time. Okay, so I hope you've got that revision. Just remember one last thing as I'm talking about measuring of this charge. Current is measured with an ammeter, and it's connected in series. It's connected in one point. We don't want to stop the show. We just want to get how many people are crossing a particular point. So it's like putting a thing on the road and everyone walks over it. Doesn't stop it. It's connected in the pathway. All the charges go through it, whereas the potential difference is connected in parallel. The voltmeter is connected in parallel. It's connected like a dipstick before and a dipstick after to try and see the difference in energy level. Okay, so having said all of that, let's do a bit of revision of grade 10 examples. Here's an easy one. Abram, I hope you've got it posted for the learners. Let's see who can be the first one to get the answer. I'm going to read it and take you through it, but if you've got the answer, post it on the page and we'll have a look and see who's getting the right one. It says, if 100 joules of work is done when 15 coulombs of charge moves through a light bulb. So you see it's taking energy to get that light bulb shining. It's taking energy to get 15 coulombs to do 100 joules of work, and it moves through in 3 seconds. Calculate the potential difference across. Notice it says across. Across means on one side and the other side, and across the light bulb, and the current in the light bulb. I want to draw a little circuit just to show you how this all works together. So if I'm wanting to measure current, I'm going to need to use an ammeter. So if I'm using an ammeter and it's connected in series to a light bulb, a circle with a cross through it indicates a light bulb. And so I'm wanting to know what the current is. Okay? I'm also wanting to recognize that I'm going to measure the potential difference. So the potential difference, I'm going to use a voltmeter. Put the voltmeter on both sides of the light bulb. So the voltmeter is now connected in parallel. The ammeter is connected in series. So what information do we know? We know that it was 100 joules and it was done by 15 coulombs. Well, guys, that's easy now. We've got the picture. We're going to say we want to know the potential difference. Potential difference is W divided by Q. And in this case, we're going to be quite clear. We're going to say, hold on, W was 100 joules. I like to just put the units there. You don't have to. Coulombs is 15 coulombs, the charge. Please don't get mixed up. It's not W or J divided by C. It's W divided by Q. When you use one of these units, you must have a number in front of it. So what is 100 divided by 15? Well, let's go to the calculator quickly, and we're going to say 100 divided by 15. Don't trust your mental arithmetic. It's 6,6666. We do to 2 decimal places, so we're going to write it off to 6,67. And the unit for potential difference is volts. So it's 6,67 volts. Hope you got that. And you see, it's quite a straightforward thing of just recognizing what you were given and what you need. Now, I want to find current passing through the ammeter. Now, let me just say something here. The light bulb, this is the light bulb, and it's connected in series to the ammeter. There's no other place for the current to go. The current is going to start at this point, at the positive. It's going to go to the negative, and it's going to go in this direction. The voltmeter itself has a very high resistance. Very little current goes through there. All of it, we say, goes through the light bulb, and so it goes. We don't want to think about any current passing through this section here. we're not going to consider. We say that current is negligible. Negligible means it's almost nothing. It's not worth taking any note of. So, what do we need to do? We need to say, if I can work out the charge, we know that we've got charge, 15 coulombs. There's the charge. And we know that it took place in 3 seconds. Hope you can see that. So 15 coulombs and 3 seconds. I think I can work out what the current is going to be. So I'm going to say I is equal to Q divided by T, and it's 15 coulombs divided by 3 seconds. And notice 15 coulombs divided by 3 seconds. Now the units here, I'm going to say 15 divided by 3 is 5. That's going to give me coulombs per second. Coulomb per second is an amp. Please note, it is not AMP. AMP must be a pop group or something, but it's not the thing that you put down next to your answer for current. Just an A. Not AMPS or anything. No, we don't want to get amped or anything like that. We just want A next to the number. 5A.
We have one mindset who got it right on the answers. Despicable moi.
Okay, despicable. Well done. That's great. I'm really proud of you. Abram,
yes.
You know what? Seeing we've got to the end of that problem, I think we just take a quick break.
I think we should do it. And mindsetters, you should always know that there is nothing that is impossible, because impossible on its own as a word has 2 words. It's I am possible. So everything is possible. Never say things are impossible. So stay tuned. I'll see you after the break. Welcome back, pre-matriculants. Now, before the ad break, John spoke a lot about energy, and here's a quote that I have to give you about energy. Everything around us is made of energy. It is up to you to attract the positive energy that comes in your mind and that comes in your life. So attract positive energy.
Hey guys, I'm not so sure about that pseudoscience, but anyway, we'll go with it for the moment. But the most important thing I know is that if you want to succeed, you've got to take what's in you and you've got to do the hard work to make it get results, okay? So I'm not going to do question 2 for the moment. Abram's posted it on the page. I want to see how many of you can get the hard work done. But don't do it now. Do it in the next ad break, and we'll come back to it after that ad break. Because what I want to get on to is we've spoken about potential difference. We've spoken about current, and we've calculated those. But what I want to get on to is finding the relationship between potential difference and current. Now, George Ohm was the man that first of all set this up, and so he recorded these results. We're going to simulate this experiment by having a look at a simulation. So you can join me, and you can go to the PhET website, colorado.ed, simulations Ohm's law, look for it. It'll look something like that. And we're going to start by investigating what happens when you keep the resistance constant. So at the moment, I've got a resistance, the R value, and I'm just going to write on this for a second. I've got the R value set at 500. This button here is the potential difference or voltage button, and I'm going to shift that up and change it. You can see at the moment we've got a big R. We've got a little V and a tiny I. The I is the current passing through this resistor. This is the resistor, and we are going to watch how that current changes. So we're going to change this thing, increase the potential difference by adding in some batteries here, and we're going to watch and see how that changes. So what's the thing that I'm going to change? I'm going to change the potential difference. So this potential difference or voltage, the V value, is going to be called my independent variable. That's the one I am controlling. The one that results is known as the dependent variable. Okay? And this R, we're not going to change. This button here, we're going to keep it. It's going to stay at 500. And even if we didn't know what it was, we're going to show you how we calculate that. Okay? So that's going to stay. That's my constant. Now, George Ohm found something else. It's not just the resistance that must stay constant, but it's the temperature. So there are two things that are constant. Temperature is one, and this thing called resistance must be constant as well. So the resistance is the constant, and temperature is also a constant. Okay, you got it. Now, what I've got on my on my notes here, let's go back there, is I've drawn up a little table just so that we can start to fill some things in and we can get some results. Remember I said to you that we're going to make sure that V is the dependent variable. The independent. So that's independent. I'm just going to put independent, depend. This is my dependent. And I want you to notice on the graph it was milliamperes. I don't like working in milliamps. They are not SI units. I'm going to change them to amperes. And I'm going to do that by multiplying by 10 to the minus 3. That means I'm going to divide by 1,000. But I'm just going to say I'm going to multiply by 10 to the minus 3. And that's not going to be difficult to put in that. And then you'll notice here, when we've got those two, we always take the dependent variable and we divide it by the independent variable, and we'll see if we get a constant. We're going to now take a look at that simulation, and hopefully we can get going with it. So look at the first reading. It says 0,1 volts. Abram, help me here. 0,1 volts, 0,2 milliamperes. Was that okay? Mm-hmm. 0,1, 0,2. I hope you've got that, because I'm now going to need to ask you. The potential difference was 0,1, mm-hmm. 0,1, and this one was 0,2. So if I divide that by 1,000, that's going to become 2 times 10 to the minus 4. Okay? 2 times 10 to the minus 4. Check it out on your calculator, and let's just do one of them so you can see that I'm not cheating. I'm going to say 0,2 multiplied by, or let's just even delete that just for a minute, to give us a second, times 10 to the minus 3. And it will give it to us as a fraction like that. And there it goes, 2 times 10 to the minus 4. Hope you can see it. Check it on your calculator. Make sure you've got it sorted out. Now, we're going back to the simulation. Now, guys, you can do this for yourself. I'm just going to put a couple of values together. I was at 0,1. I'm going to double that. I want to get to 0,2. There we go, 0,2. Now, what's nice about a simulation is that I don't have to worry about temperature, because this is all keeping the temperature the same at the moment. So 0,2, what's happening to the current? 0,4. Let's fill it in. So 0,2, 0,4, which is 4 times 10 to the minus 4. Okay? And so I could carry on. And I just wanted you to see that I could double it again, or I could just pick another value. Let's pick 2. So there we go, 2 volts, 4 milliamps. Normally, if we were doing it and we had lots of time, we'd take them up in even steps, but we haven't got time to do that tonight. We're going to say, let's get to 2. This one was 4. Now, notice what this is. It's 4 times 10 to the minus 3. Okay, let's pick up another one. Let's take it up. Let's take it up to 4. There we go. 4, 8. Hey, guys, I hope you can see that there's a pattern here. So I double this one. If I double this one, what happens to this one? It doubles. I hope you can see that. There seems to be a relationship. As the one increases, the other increases by the same proportion. Have a look at that. Just for a second, take a notice that I multiplied by 2 there, and I've multiplied by 2. I multiplied by 2 there, and I've multiplied that by 2. So as the one goes up, it's not just the other one's going up any old how, it's going up by the same proportion, by the same factor. So let's test it. If I multiply 2 by 3, that will give me 6. So let's have a prediction here. If that's 6, what do we think it's going to be? What's the output going to be? If we can get the potential difference to 6, what do we predict? Remember, that was multiplied by 3. Have you got any idea what my answer is going to be there? I've got 4 to start with. What's my answer going to be over here? Multiply that one by 3. What must I do for 4? I predict it's going to be 12. Let's check. 4 times 3 is 12. Let's check if we can get there. So I want to get it to 6. If it will let me get to 6. There we go. See, it's 11,4. It's almost there. 6, 12. Yeah, I got it. I was right. Now, guys, I didn't practice that. Abram, did I practice it
No,
before?
you didn't.
No. I'm just reading the data. I'm understanding that there is a relationship between current and potential difference. Now, guys, if you go over here and we now fill in that, what we need to recognize is that's 12. Now, we could say that's 1,2 times 10 to the minus 3. Now, very quickly, whenever you get this sort of thing in a graph, in a table, you're usually going to be asked to draw a graph. So, what's the graph going to look like? And I'm going to quickly just sketch some axes here. So there's my one axis, and here's my other axis, and I should really put some arrows on. So let me get back over here, and I'm going to put an arrow on here that says that, and an arrow that says that. Now, on your graph, where does your independent variable go? The one that you control. Now, guys, this is important, because you can't just decide, oh, I'd like to put the one on the... The independent variable goes on the horizontal axis. The one you control goes at the bottom. So this one is V. This one is the one that I control. This one was I. Now remember, we measured it in milliamps, but I said for SI units, you must make it amps. So if we make it amps, then we're going to get that sort of situation. So we've got I and V. What do you think we're going to get? Well, if I started to plot it, what I'd find is that I get a straight line. Now, this straight line is going to be somewhere around there. How do I know it's not going to be that steep, or it's going to be quite flat like that? Well, because if I look at this value here, the I divided by V, the I divided by V is my gradient of that line. And I'm just going to do it for 1, because as a straight line, you can test it. You can take all of these I values and divide them by V values. I'm just going to do it for 1 so that you can see. And there's the one that I've got. I'm going to say 2 times 10 to the minus 4, 2 times 10 to the minus 4. I'm going to divide by 0, 1, divide by 0, 1, and I'm getting an answer of 1 over, I just want you to see that. It said 1 over 500 on the calculator there. 1 over 500. I'm going to write it like that, and then I'm going to write it differently as well. So this one says 1 over 500, which is equal to, let's try the next one. We'll do one more. Let's try this one over here, the 1, 2. 1, 2 exponent -3, and we must divide by 6. Do you agree? Divide by 6, yes. Look, I think have I made a mistake? 1, 2 times -3, because it's giving me something strange here. I think I might have made a little bit of a mistake. Oh, it was 12. It's times 10. Look here. That's what I didn't do right. Very good. I picked it up. This is 1, 2. That was one. I've made a mistake over there. So this is not going to be times 10 to the 12. It will be 12 times 10 to the minus 3, which isn't the same. So let me correct that. So there we go on the calculator. Good thing I did it. So there we go. 12 exponent -3, because it was 12 milliamps divided by 6, And there we go. Also, 1 over 500. As a fraction, it's 2 times 10 to the minus 3. So this, all of these values, you can check them, will end up being 2 times 10 to the minus 3. 2 times 10 to the minus 3, which is the same as 1 over 500. Now, guys, if you look at the graph, the gradient of this graph is the change in I over the change in V, which is equal to 1 over 500. What's interesting is if we go back to the simulation, you'll recognize over here that we said the resistance is 500. So, by definition, we actually could define resistance, and this is what Ohm said. He said, guys, let's do it that way. Let's rather go this way around, and let's say V over I. And so you could do V over I, and we get 500 here. 500, 500, all the way down, and you can fill it in yourself. So resistance is constant. As I increase the current, or as I increase the potential, the current increases, but the resistance stays the same. And I get the straight line graph that passes through the origin. That's how Ohm defined it. Now, last thing I'm going to say now, before I hand it over to AB, is not all resistors are ohmic. Ohmic resistors obey Ohm's law. After the break, we're going to come back and just formally tie up those loose ends.
Right, thank you so much, John. Mindsetters, keep the questions coming, because after the break, I'll also take some of the questions that I've seen on the Facebook page. If you're not there yet, be there. Facebook.com/LearnExtra. Now, when life meets science, it says every time when you subtract something that is negative into your life, you attract more positive things in your life. So see you after the break. Welcome back, Mindsetters. Now, going over Facebook, we have some questions, but also I just want to start with this one from Ritla. It says, hello, grade 11s. It's so easy to pass your subjects. Success is not the key to happiness, but happiness is the key to success. If you love what you're doing, you will be successful. What do you think of that, John?
Yeah, I agree with that. I think, it's all about motivation. Don't give up, guys, and enjoy what you're doing. That's what National Science Week is about, to show you how amazing science is. So get along, find a place near you, get involved in finding out about careers in science as well. That's really important.
It's all about being happy. I have the questions for you.
Okay,
talking about
excellent.
Happiness.
So you're very happy.
Yes, I'm so happy.
Okay, let's go for it.
Right, here's a question from Tabang Fukeng. It says, I can obviously see Abram, but can I ask is this graph going to help us in any way, and what is the relationship it shows us?
Okay, excellent question, Tabang. Now, guys, this is a fundamental graph. This graph tells us about a special type of relationship. Now, I'm going to turn it around for you and show you Ohm's law as it's traditionally stated. And I want you to pick up the difference between the graph I drew and the graph as it's drawn here. So look at that while I'm explaining. So here we go. So to answer Tabang's question, in words we'd say, according to Ohm's law, the potential difference over a resistance is directly proportional. There's the word that you're needing. That's the relationship. Remember, I explained it to you. As the one increased by a certain proportion, the other increased by the same proportion. That's what we're talking, directly proportional. Doesn't you mean as the one goes up, the other goes up? No, that's not necessarily directly proportional. As the one increases by a certain amount, a certain factor, if you have to multiply the 1 by 3, then the other variable, the other output variable, increases by the same proportion. So that's what it's saying. As the potential difference is directly proportional to the current through the resistor, provided the temperature of the resistor remains constant. Now, even though we state it like that, we could state it the other way and say, for example, we could say the current passing through a resistor is directly proportional to the potential difference provided the temperature remains constant. Traditionally, and the way that Ohm did it, he measured current as his independent variable. He therefore measured potential difference as his dependent variable. And he then defined resistance in this way, to say resistance is the gradient of that slope. Resistance here is constant. Why? Because the gradient is constant. Notice it's a straight line and it passes through the origin. Now, you've got to identify that. In physics, there are a whole lot of directly proportional relationships. And they're really nice because they provide us these constants that we love working with. So get to know them, get to identify them, because they give us these simple equations that we can use to find really interesting results from. So that's the importance of it. We can use this now to calculate unknown quantities of either resistance or current or potential difference. If we've got two of them, we can find the other. Because in mathematical terms, when we say something is directly proportional, then we say V is directly proportional to I. We can't do anything with it. But if we say V equals I times a constant, then we can change the directly proportional sign to an equal sign. We can do that because the graph shows us that there's a constant gradient. If the gradient wasn't constant, it wouldn't be possible to write an equation like this. I hope I've answered that question. Okay.
And then Katla is asking that, can you also give that relationship in words?
Okay, I've just done it. There's the words. The potential difference over a resistor is directly proportional to the current through the resistor, provided the temperature of the resistor remains constant. So guys, there you've got the meaning of it, you've got the mathematics of it, and you've got it in words, and it all sums up. But remember what I said to you before the break. Not all resistors follow this pattern. Not all of them. Those that follow this pattern are called ohmic. But there are others that do not follow this pattern. So an ohmic resistor obeys Ohm's law at all temperatures. But non-ohmic resistors, a non-ohmic resistor does not obey Ohm's law. Its resistance changes as the temperature of the conductor changes. So if you've got something like a semiconductor, for example, at low temperatures, a semiconductor will not act as an insulator. It'll have a very high resistance. Hardly change. As it heats up, it drops its resistance. As the temperature increases, it decreases resistance. It's a special type of non-ohmic conductor. A light bulb, as you increase the current passing through it, it heats up. And what happens at higher temperatures, its resistance increases, opposite to the semiconductor. So there are two examples of non-ohmic resistors that I've just given you, a semiconductor and a light bulb. They do not have a constant resistance. It needs to be at constant temperature. Problem at light bulbs is their temperature gets so high. At very high temperatures, metals increase their resistance. Okay, so I hope I've clarified that. Make sure you follow that. Check for examples in your textbooks as well.
Here's a quick question for you, John.
Give me another one.
From Livinia, all the way from Lesotho.
Yeah.
Livinia says, I'm always getting confused by the difference between voltage and potential difference. Can you please help me on that?
Okay. There is an important word that you need to understand. Voltage is volts. Let's just clarify it. Volts is the unit for potential difference. Voltage is another word that means exactly the same as potential difference. And there's a third word that you need to know that's called EMF. And I'll come to that in a minute. Those all three have the same sort of meaning. Now, Abram, I put up question 2.
Yes.
Earlier. Has anybody answered it?
There's about 30 people that have answered the question.
Okay, let's see if they've got it right. Because I don't like to give a problem and they're not given an answer. So it says, if the potential difference, another word of saying that, if the voltage across a resistor is 12 volts. Okay, potential. How much energy is transferred in 10 seconds when 40 coulombs of charge moves through the resistor? Wow, that's quite a tough one. So what we've got to recognize, we're wanting potential difference is equal to work over charge. Now, notice something here. Work is the same as energy, and we're wanting work. So I always prefer to substitute. If the potential difference is 12 volts, I'm going to just put the 12 on its own, and then I'm going to say it's transferred in 10 seconds. I don't need that 10 seconds. When 40 coulombs of charge, so 40 coulombs of charge moves through the resistor, what's the work done going to be? Well, it's not difficult. It's W is equal to 12 times 40. And that's going to give me an answer of 480. Now, what? Work is measured in joules. Let's just check it very quickly. So 12 times 4 is 48. 480, that's correct. We know that it is correct. Let me just make sure that you can see that. Pull it up for you. Is that what the answer that most people got?
That is the answer.
Okay, excellent. Well done, Mindsetters. You're on the queue. You've got it sorted out. Now, let's skip forward because we've done Ohm's law and we want to hit some more questions. So, here we're going to apply Ohm's law. It says, if the current passing through a resistor is 3 amps and the resistor has a resistance of 4 ohms, what is the potential difference across the resistor? Now, I like to sketch little diagrams. So I'm going to do a resistor and I'm going to say I want to know the current. So I'm needing an ammeter. I'm going to draw the voltmeter in parallel across it like that. And I'm going to say I know that the current I is equal to 3 amps and the resistance R here is equal to 4 ohms. I want to know what the reading on the voltmeter is. So draw my little sketch. How am I going to do it? Remember, R is equal to V over I. That's Ohm's law formula or equation. R is equal to V over I. Let's substitute now into that equation so we can get things sorted out. And we can say we want to get R. We know R is 4. We know that V is the unknown. 3 is the current. So what are we going to find? We're going to say V is equal to 4 times 3, which is 12. Don't forget the unit volts. Got it? Check it for yourself. Make sure that you've got that right. This is an application of Ohm's law. Okay, next. Here's the next question, question number 4. It says a resistance has a resistor of 10 ohms. Calculate the current passing through the resistor. We want to know when the potential difference across the resistor is 5 volts. So again, R is equal to V over I, and we're going to say V is 5. The current we don't know. The resistance is 10. So what are we going to do? Surely we're going to multiply both sides by I and divide by 10, and we get 5 over 10, which is giving you a half an amp. Okay, and there you go. If you want to check that it works, do any of the other combinations. I always remember V is equal to I times R as an alternative. So I'm going to put it back and I'm going to say I is 0,5. So look, I'm just substituting back just to check. V is equal to I times R, and I'm just checking. I'm saying 0,5 times the resistance. The resistance was given as 10, and half of 10 is going to be 5 volts. And what do I know? It was 5 volts. So I know I'm correct. So guys, there are ways to check yourself to make sure you've got it right. Okay, we're moving on because we've got a few more things to talk about. We've already introduced the idea of series. In a series circuit, everything follows each other. So these resistors are in series. There's only one path, the blue line that is going through here, and I'm going to highlight it in pink as well just so that you can see it. That is the circuit. The current is going from positive to negative, and I've just made that. What I'm going to recognize is that they follow each other. Now, the current in a series circuit, I, is the same. It's not going to change. It's going to remain the same. The resistance, we can add up R1 plus R2 plus R3. What that also means is that if I say R is equal to V over I, the current is the same there, then I can take this potential is going to be proportional to the resistance. So if R1 is a big resistor, the potential difference across it will be large. We recognize resistors in series are potential dividers. So we'd add them up and we'd recognize that each of those apply. So I hope you can see that the other relationship is that V total is equal to V1 plus V2 plus V3. And I'm going to say it again, that I total is equal to I1, which is equal to I2, which is equal to I3. And it's the same everywhere. Doesn't matter where it is. It's the same. That's in series. Now, let's look at resistors in parallel. So here we go. And this is really quite interesting, because what you have here is you've got the total current, I total, and it divides. It can go in two parts. In fact, in this case, it can go in three. It can go up through R1, and then it comes back down again and joins together. There's another branch. We call that second path a branch. And there's the third branch. So I hope you can see that the current is dividing. Here, the potential difference across those three resistors is the same as across the branch. So V branch is equal to V1, is equal to V2, is equal to V3. The current divides. And the last thing that you need to know is that to work out the resistance, we're going to use this strange looking formula, which has got fractions in it. Please be very careful when you do, because that's where lots of learners make mistakes. If we're looking for R1 over R total or 1 over R equivalent, in other words, what could we do to take this branch and replace it by a single resistor? Then we put it as 1 over R1 plus 1 over R2 plus 1 over R3. Okay, now I won't have time to do question 3, but we'll pick up on more complicated ones next week. Okay, quickly, in the last 2 minutes, I just want to remind you that power is the rate of electrical energy conversion. So power is like work, the rate of work being done. But in electricity, we've got these formula that are used to calculate power in a circuit. Use the correct one depending on what information you're given. Each of these is correct. They just have used Ohm's law to move from that one to that one. So in other words, if we want to get rid of I, we would say I is equal to, what's it going to be? R is equal to, remember, R is equal to V over I. So I is equal to V over R. And if you substitute that in, you'll be able to see how those two work together. Because that is a result of that equation. Okay, so if you look at V, in fact, that's the one that's substituted there. If you look at V, V is equal to I times R. You substitute that one in, you'll get that equation. Last thing in 1 minute. Oh, we've gone out of time. I'm sorry, I was trying to get there. You try it yourself. Thank you so much for being with us today. I hope we've covered everything. Abram, it's been great being with you.
Thank you so much, John. Same here, and to all the Mindsetters, the grade 11s, thank you for tuning in. Remember, if you still have some questions, email them at helpdesk@learnextra.co.za or via our Facebook page, and we shall be there to help you.
On the web page too.
Yes, on the website. But thank you very much, Mindsetters. Keep it tuned. Learn more, learn extra.
over circuits. They've traditionally been in the grade 12 exam. I don't see why they won't be in next year. So guys, pay attention. We're dealing with some other interesting characters this afternoon. We're dealing with not Michael Faraday, but George Ohm. And George Ohm, he has a whole practical experiment that you're going to need to do in class as a practical. If you're not sure about it, we'll cover it here, so don't go away.
All right, don't go anywhere. Here's your toolkit. All you need to do, number one, is to join us via Facebook. Our Facebook page is facebook.com/LearnExtra. You should be knowing it by now. We have more than 48,000 likes, and you can join the crew, join the club and our community, and let's get chatting and also help one another on the page. Secondly, join us on Twitter. Follow us at LearnExtra. We'll try and read some tweets as the show progresses. And lastly, you can download your notes all for free on our website, which is learnextra.co.za. And now, beginning this lesson, here's a quote from a mindsetter who just said earlier on, please, AP, may you share this quote for us? It says, not that I'm a genius, but one thing I always try to do is that I spend most of my time trying to deal with the problem. So try to deal with the problems that we are facing today on a positive note.
Excellent. Now, guys, if you've got problems, there's only one place to go to get the answer. That's the help desk. And we're starting a new way of doing the help desk. So get onto the website and fill in the form for the help desk. It's help desk on the web page. Get the form filled in, and we'll be taking your responses there. The other thing that I wanted to mention just briefly as Abram was going through his stuff is that you really need to make sure that you download the notes. Some guys have sent to me on the help desk, hey, download the notes. How do we do it? We're not sure. So what I want to say to you, you get onto that website and you look for the blue box. It says notes in it. Click on the blue box and you will get the notes. Okay, so don't forget that. Today, electric circuits, let's go. We're not spending a lot of time on the introduction, but in this lesson, what we're going to do is we're going to look at the three basic things relating to electricity. We're going to discuss current, potential difference, which is also called EMF. We're going to look at Ohm's law. We're going to explore that. We're going to talk about ohmic and non-ohmic conductors. We're going to look at resistors and how they're put together in series and in parallel. And we're going to look very briefly at power in a circuit. So you can see there's a whole lot of stuff, and I better stop talking because I can get carried away and I want to get through the stuff that we need to get through. So let's get our heads down and let's get going, because some of it's a bit of a revision. So let's start. Well, what do we understand by current? Everyone says current, you must beware of current. That's true, because current, what is current? Abram, you got any idea? What's current?
I say it's electricity.
Electricity, called conventional current, which we will define a little later. We'll say conventional current. In fact, we defined it last week, if you remember. It's the movement of positive charge from a positive to a negative. And we're going to use this formula. I is equal to Q divided by T, where Q is the charge and T is the time, to work out the strength of the current. So if we've got lots of charge in a small period of time, it's like walking the talk. I don't know, did you participate on Sunday? There was a big walking race or a competition.
I saw that one.
You saw it?
One, but
okay, so guys, I was part of that. Crowds walking past a position along with the deputy president of the country. I was there early in the morning, and we walked down the road. And sometimes the road couldn't hold everyone because there were so many people passing a particular point. Okay, earlier in the 15 and the 20-kilometer race, they were more spread out. So you had fewer people passing a particular point. The current wasn't as strong. Come to the 8K walk, which I walked with along with another 22,000 people. We moved quite quickly, but a lot of people covered a short distance. It was like a high current. If you just stood there, people would almost push you forward. You'd feel the current. Okay, now, what is potential difference? Potential difference is defined as followed. Potential difference between 2 points in a
Matriculants, welcome to it. This is Learn Extra Live with me, AB, Abraham with John. How are you, John?
Abraham, I'm really good, and it's a pleasure to be here again this afternoon.
Likewise, it is National Science Week. I hope all the Mindsetters are doing something at their schools or just in their classroom, or even right now as you're joining us. I hope you're doing something that has to do with science.
Yeah, absolutely. National Science Week, great opportunity to look at science careers. And I mean, if you're in grade 11 and you're doing physical science at school, must be on your priority list. Hey guys, if you're getting good marks, get into the universities, find out when their open days are, because you need to get your applications in early next year. So don't be restricted, and remember, most of those faculties are going to take your grade 11 marks as entry requirements. So put in the hard graft now.
It starts now. Talking about that, let's start now. What are we talking about today?
Okay, so Abraham, what we're doing is we're doing electric circuits. Now, electric circuits, I love circuits. They're just amazing. You remember last week we spoke about electromagnetic induction, electromagnetism. Now we're going to move on to something that you're going to get in your matric exam. I can promise you now, even though the exam requirements haven't finally been written for your matric exam for next year, they're going to have a circuit. They've had them for the last, I don't know how many years. So you need to study this, because you might not have time next year to go. Not sure? Okay, so guys, what we're talking about, electricity is a movement of charge. Current, in revising from grade 10, we say current is a flow of charge that is either positive or negative charge. So what we've got to make sure of is that when we talk about current strength, how strong is a current? When you talk about currents, maybe you're thinking not just of electric currents, but of currents in a river. You know that if you dive into a river, you'll be swept downstream by the flow of the water, the movement of the water. Or if you're in the sea, you can get swept out to sea, even though there are waves coming in, by currents in the ocean. And they're very dangerous. That's why we have lifeguards on the beach. So it's a movement of water in a particular direction. Now, in terms of our current in electricity, it's a movement of charge. Now remember, there are both positive and negative charges in every bit of matter. The positive charges, objects, are called protons. So they're known as protons. And the negative charges are known as electrons. They come from the atom. Now, the actual protons don't move. They stay stationary. But because the negatives are moving over them, they move it kind of gives the impression that the positive region of charge moves in the opposite direction to the negatives. That's why we have something